In this slide, we will show how to have a control of numerical errors in problems, but you should know that there is no schematic and general approaches to evaluate the numerical errors for all problems. So based on the problem type, the approaches can change, but in many cases there are some suggestions. We will show you these suggestions here. And in many cases, the error estimates are based on the experience and judgment of the engineer. Usually you know about the problem because you have some experience, and based on that you make some judgments. And some guidelines for error analysis are over here. First of all, try to avoid subtracting two nearly equal numbers because they can reproduce some values very near to zero. And that's why the loss of significance almost always occurs when this is done, and you will have very small values near zero, and it will be a problem. Also, sometimes you can rearrange or reformulate the problem to avoid subtractive cancellation. So subtractive cancellations, we don't want them, so we don't want to subtract two values. That's why you can try to rearrange the problem formulation to avoid this, to eliminate this. When adding and subtracting numbers, it is best to sort the numbers and work with the smallest numbers first. This avoids loss of significance. So starting from smallest numbers, try to add or subtract numbers. So that's why you need to put them in an order from small to large to have an operation. The fourth suggestion, predict total numerical errors using theoretical formulations. So if you have them, of course. Taylor series is our primary tool for analysis of both truncation and round-off errors. You can try Taylor series initially. 5. Prediction of total numerical error is very complicated for even moderately sized problems and tends to be pessimistic. Therefore, it is usually attempted for only small-scale tasks. So try to have the numerical error calculation or prediction first for small-scale tasks. And if you are confident on them, just use it for the large problems, because if you try to use that in the large problems, you can have bad results and have a pessimistic opinion. 6. Push forward with the numerical computations and try to estimate the accuracy of your results. This can sometimes be done by seeing if the results satisfy some condition or equations as a check, or it may be possible to substitute the results back into the original equation to check that is actually satisfied. So this sixth suggestion can be based on your experience, because you just go ahead and calculate or make the numerical computations and try to estimate the accuracy. You can use approximation error for this as well. 7. You should be prepared to perform numerical experiments to increase your awareness of computational errors and possible ill-conditioned problems. And for this, repeating the computations with a different step size or method and comparing the results can be a good alternative. If you know different numerical approaches, you can try different approaches and see the results. Also change the step size to see how the errors are changing or the results are changing. Let's say if the result doesn't change too much, that means you are in good way. Sensitivity analysis to see how our solution changes when we change model parameters or input values. So you can simply change the input values, see the results, or change the model parameters, see the result, make a comparison to see if, for example, one input value, when you change it to another value, the calculation will give very similar result. That means the actually calculation is not sensitive to that input value. Then you can just ignore that input value maybe, or based on that you can evaluate some sensitivity. Try different numerical algorithms, as we said earlier here as well, different methods or algorithms that have different theoretical foundations. Here, different theoretical foundations, and are based on different computation strategies or have different convergence properties and stability characteristics. Simply try to have different alternatives to make an assumption or a prediction for the problem, so that you can make some interpretation between the numerical methods and see which one gives a good result, and you can have some evaluation of the numerical errors. We do this because initially we assume that we don't have in real life, we don't have the actual problem formulation, let's say. That's why we use numerical approaches, and that's why we need to control the numerical errors based on these suggestions. So up to here, we talked about the round-off errors and truncation errors, but we will also have some other errors as well. And blunders are one of them, and these are also called gross errors. Blunders are actually happening because of the malfunctions of the computers or human imperfection. So basically we make mistakes, or computers make mistakes, and we will have some errors. So these are called blunders. And how can we avoid the blunders? Simply, we will need to know about the fundamental principles in a good way. We need to have a good knowledge of the fundamental principles so that we don't make any mistakes. Or the computer also should be coded well enough so that it doesn't make any mistakes. And care with which you approach and design your solution to a problem. So being careful, a high care is important. Good programming habits like the well-structured programs can eliminate the blunders, can eliminate the issues with the computers. Also, checking whether a particular numerical method is working properly is important. You can make mistakes on developing the codes of numerical methods, or the numerical method may be not suitable for one problem, and that's why it can give error, and you can eliminate these if you know about the limitations or the behavior of the numerical method for different problems. We need to check these, and these will reduce the blunders. Another error type, apart from the round-off error, truncation error, and blunders, is the formulation errors, or we call them as model errors. These are simply errors which are because of avoiding or ignoring some physical aspects or some theoretical aspects, which can be considered a very small effect on the results. So a bias that can be ascribed to incomplete mathematical models. For example, for the Newton's second law, you know that F equals ma, and F and the acceleration is dependent on each other with the mass. So these are actually ignoring some relativistic effects. Let's say we ignore the drag of the air while moving in the road, on the road or in the air. But these are very minimal effects. That's why, although these are creating errors, the errors are minimal. That's why we will have some model errors, or we can ignore the friction, for example, in a problem. However, suppose that air resistance is a function of a square of velocity instead of being linearly proportional to it. If you remember, in the parachutist example, we have an air resistance, and the velocity was only linearly proportional. It was only v value. But in reality, it can be v square. And in that case, if we ignore that, the air drag resistance just eliminated from the calculation, then we can have a problem if it is dependent on the square of the velocity. Then the solution would be erroneous because of the formulation error. We need to be careful about these. So the assumptions that we make for generating the actual theoretical formulation basically creates model errors in summary. In this slide, we will talk about the data uncertainty, and specifically the uncertainty term actually means errors, but the error when we make repetitions of tests or measurements, if we have different results, that kind of error is uncertainty. For example, we want to test a falling parachutist and try to measure its velocity. So we can repeat the jumps, let's say 10 times. And each 10 times we measure the velocity slightly differently from each other. And these differences brings us an uncertainty in the measurement. This is an error, but the error in a repeated measurement, let's say. And each repeated jump will give a slightly different measurement. That's why the uncertainty exists. And if the measured velocity is consistently under or overestimated, then we have inaccuracy. We say that we have an inaccurate measurement. If the measured velocity is randomly low and high, then we question the precision actually. So for the control of uncertainty, we use some statistical methods to quantify this repeated measurement error or data uncertainty. What we do is we have a number of measured data, and we simply have an average of it, which is called mean of the data, the location of the center of the distribution of the data. And also we will have a degree of spread of data. This can be considered as the standard deviation, for example, or variance of the data from the center point. And during this class, we will assume we have not made gross errors, blunders that we mentioned earlier, and we have a sound model, so we don't have any model uncertainty. And we are dealing with error-free measurement, so we don't have uncertainty or errors due to the repeated tests. We don't have any error because of that. But this is an important factor and should be considered. And maybe to be able to learn about this a little bit more for the statistical methods to control the uncertainty, you can consider taking a statistics class to have some knowledge about it. So in the chapter 4, we learned about truncation error and the Tyler series to be able to understand the truncation error, and the Tyler series to use for approximation of differentiation or derivatives, as well as the blunders, which are different other error types, blunders, model errors, and uncertainties. And for further understanding, you can read your book, chapter 4, and have some further information. Thank you for listening.